In this video, we are going to study Einstein's formulation of the equivalence principle. This formulation is usually known as the equivalence principle and also as the medium-strong equivalence principle. This last name, medium-strong, makes reference to the existence of a weak formulation and a strong formulation of the equivalence principle. The weak equivalence principle we have already studied, and we will study the strong equivalence principle at the very end of this lecture. But before we formulate the Einsteinian equivalence principle, we are going to motivate it and give some physical arguments, some of them based on thought experiments that support it and that lead us to formulate it in precisely that way. We are going to start thinking on the weak equivalence principle, and okay, if you think hard enough, maybe you will arrive at the conclusion that it seems to suggest that there is a relation between gravity and properties, general properties of space-time. Why is this so? Well, space-time is the only structure that affects all physical systems, because all physical systems take place or work in space and time. And the weak equivalence principle is a general property of the motion of all particles. So there is some relation between these two things. You may believe that the properties of space-time somehow dictate this motion, okay, under the effects of gravity. So now let me go back to Minkowski space-time, okay, just to support this idea. Minkowski space-time, remember that is space-time, so the set of all possible events together with the Minkowski metric. This Minkowski metric has many properties. In particular, it was invariant by definition under the whole Poincaré group, which includes space-time translations. And you know what a free particle does here. Okay, it moves in a straight line. Okay, this is the motion allowed by the laws of conservation of momentum that are imposed by the structure of Minkowski space-time. If you don't have momentum conservation, you don't move in straight lines and vice versa. So it is the properties of Minkowski space-time that dictate how particles move. So let's think now on some other kind of metric that now we assume that generalizes the Minkowski metric that includes gravity. Okay, so gravity is included here. This metric will dictate the conservation of some quantities and maybe the non-conservation of some other quantities, but then if you study more or less in the same way we study the motion of a free particle, free from the point of view of any other interaction, okay, in this metric, so this is not a free particle, but it will be a free-falling particle, because the only thing that acts on it is the structure of space-time dictated by this metric, and we may think that this structure of space-time is conditioned by the fact that there is gravity in it. Then there will be some general motion, but one thing is clear is that this motion will be the same for all particles, because all of them move in the same metric under the same laws. So motion in a metric, okay, free falling motion in a metric implies the weak equivalence principle. So this idea that the weak equivalence principle tells you or suggests that gravity is related to the properties of time is well, is satisfied at least in this direction. if we assume that gravity is described by some metric, by the properties of space-time, then a free-falling particle, which will be a free particle moving in this metric, will always have the same motion, independently of its properties, the kind of its composition, and so on. Okay, so this is the first step towards the formulation of the Einsteinian equivalence principle, but this principle also talks about the rest of the laws of physics, and we have to add them to the picture, because so far we are talking about free falling particles only, and well, we need to know what happens when they are not free falling anymore, but that they are subject to other forces, other interactions. However, observe that so far we only know the laws of physics in inertial reference frames, and this is okay, Minkowski space-time, so it is in absence of gravity. This is what we know about all the laws of physics. We know what they are like in absence of gravity, or what is the same in inertial reference frames. And if we want to include the rest of interactions into the picture, into this picture in which gravity is described by a metric, and everything will take place into this new space-time described by this metric, including the rest of interactions, we need to know what these other interactions are like in the presence of gravity. And we are going to do this into several steps. First, we are going to reinterpret the weak equivalence principle in a slightly different way. So we could say that the weak equivalence principle can be formulated in this way. If an observer is in free fall, okay, with the rest of the particles, the test particles that we are studying, this observer in its reference frame, which may not be an inertial reference frame, because if there is some gravitational field, probably it is accelerated with respect to an inertial reference frame. The observer in this reference frame will see those particles moving in straight lines, or not moving at all if the initial conditions of those particles, those test particles, are the same initial conditions as those of the observer. However, motion in a straight line, or motion at all, is exactly the same as motion in Minkowski space-time, as we have just reviewed a second ago. So we could say that this implies that you can eliminate the gravitational effects, the effects of the gravitational field on the particles, by going to a non-inertial reference frame. Which one? And in a reference frame in free fall. Gravity disappears in this frame, and this reference frame in free fall would be the reference frame of the observer in free fall. So we can say this gravity disappears, or gravity is cancelled by the acceleration of this reference frame. Okay, let me say it in this way. So gravity can be cancelled by the acceleration of a non-inertial frame. These accelerations, as we know, give rise to what we usually know as inertial forces. Okay, maybe a better word would be non-inertial forces. These are forces due to the fact that, or apparent forces which are due to the fact that the system is accelerated. But let me now go to put it in a different way. You could also say, by the same token, okay, we have cancelled the gravitational field, but we can also say that the gravity can be replaced by an accelerating frame. In this case, if you want, we are inducing, in the case 3, we are inducing a gravitational field which is opposed to the natural gravitational field. However, we could start from other situation in which there is no physical gravitational field caused by masses, and if we accelerate, everything will move in exactly the same way, and we will say, okay, this is because inertial forces act on all the particles in this non-inertial frame in exactly the same way. But this is exactly the property that distinguishes the gravitational field according to the weak equivalence principle. So putting everything together, you arrive to this conclusion that gravity is equivalent to inertia. Okay, it's equivalent to inertia in this way because inertia is dictated by your metric and the properties of your space-time. It is also equivalent to inertia because inertial forces have exactly the same properties as gravity, so they satisfy this weak equivalence principle. Also because going to a non-inertial frame, you can also remove gravity completely. For all these reasons, you would conclude that gravity is equivalent somehow to inertia, and this is what the Einsteinian equivalence principle tells you, okay, that gravity is equivalent to inertia. So in the weak equivalence principle, the equivalence was between gravitational mass and inertial mass only. Okay, we formulated it in a more sophisticated way, but basically it was just that. Here Einstein went much further than that. Okay, it's all gravity or phenomena related to gravity, or the very own nature of gravity is the same very own nature as inertia. Now all this still refers to free-falling particles, or absence of any other interaction. Then what Einstein did, and this is the Einsteinian equivalence principle, was to include other forces in the picture, saying that if you are in a free-falling frame, all laws of physics take their special relativistic form. Okay, we have basically said here, one way or the other, that what an observer in free fall observes is Minkowski spacetime. And now we also said that we know the form of the laws of physics in Minkowski spacetime. Okay, it could be or not that the laws of physics are the same in this, supposedly Minkowski spacetime, because it is not inertial, it is not an inertial reference frame. Okay, but it turns out that this is what Einstein says, that in this Minkowski spacetime that a free-falling observer sees, all the laws of physics take exactly their special relativistic form. Now, if you know what is the form of these special relativistic laws, then, and you know how to transform your coordinate, your reference frame to an inertial reference frame with gravity, in which gravity is put back into the picture, or to any other reference frame, you will know what the form of the laws of physics are like in these other reference frames, or in presence of gravity. So this is the key to reformulate everything in the presence of gravity, to assume that when you remove gravity, but you remove it not because there is no gravity and because you are in an inertial reference frame with Minkowski spacetime, but because you are in a free-falling frame in which you have a Minkowski spacetime produced by this free fall, the laws of physics take their special relativistic form. So now two problems that this principle has. I mean, this is a principle and a full program to reformulate all the laws of physics, so that they include their form when they are coupled when there is gravity present. So the first thing that we can say is that we don't know how to do exactly this change of the necessary changes of coordinates and take into account non-inertial forces, because we know how some things work when we perform Poincare transformations, but not just any other coordinate transformation. So we will have to invent a formalism that takes into account, or that allows us to make any arbitrary change of coordinates, and that takes into account properly inertial forces. The second observation is that we said that we can make disappear all effects of gravity, but this is not exactly true. If you draw the Earth like this and you have a free falling observer and whatever free falling thing in this direction, any other free falling observer will suppose that they start at the same time, they will see that they are getting closer and closer. Okay, so and they can deduce that there is some gravitational force and that they are falling in it, even though each of them does not feel any kind of acceleration. Okay, these apparent forces that tend to approximate these two observers are called tidal forces. Another observation would be that if you fall maybe in the same direction, but you start falling here and you start falling here, since the acceleration here and here are different because this gravitational field is non-uniform, then they will start separating because the acceleration of this guy is much larger than the other guy, even if they start at the same time at rest. Okay, this is also a manifestation of a tidal force. These are two of them, and this is due to the fact that most gravitational fields are non-homogeneous, are not homogeneous. In fact, most physical gravitational fields, or all gravitation, are not homogeneous. And an idealized situation in which things fall parallel, it is only approximately true in the surface of the Earth or in a very small region. Okay, the moment you realize that the Earth is a sphere and you take into account that, this is not satisfied. So it is satisfied approximately if you consider as a very small region, and we will have to consider to include a condition saying that this principle is only satisfied in very small regions of space and time, because if you consider also periods of time which are large enough, you will start observing tidal effects. So as a conclusion, the Einsteinian equivalence principle will be only valid locally in space-time. In small neighborhoods, this will be enough. And another conclusion is that the gravity does not entirely disappear from the picture. That would be maybe too much. Okay, so gravity is still there, but they're only through their essential manifestations, which are tidal forces. And now we are ready to formulate this principle more rigorously. Well, we are now ready to state precisely the Einsteinian equivalence principle. Well, here it is. Let me read it just in case my handwriting is not good enough. So around any event of the space-time, there is always a sufficiently small neighborhood such that in every local freely falling frame in that neighborhood, all the non-gravitational laws of physics take their special relativistic form. And now that we have read it, let us go back to this formulation and let us try to understand all the subtleties involved in this formulation. Okay. So first of all, you see here any event of the space-time. This means that this happens everywhere in the universe at any point. Okay, and this law that the laws that satisfy this principle, etc., will satisfy these properties at any event of the space-time. So there is independence of time and space. Okay, the laws of physics are the same everywhere in the universe. At least they agree with properties that they have, that they agree with this principle is true in any point at any time. Okay, the locality of this formulation is expressed through this sufficiently small neighborhood. Okay. How small? Well, as small as you need for this to be precise. So if you want this statement or the measurements that you make to be even more precise, okay, and avoid the tidal forces and stuff, then you make it even smaller, and that's it. Okay, and then every local freely falling frame means that, okay, in such a point you can define many freely falling frames depending with different initial speeds. If you want, they may have the same acceleration because they are freely falling, but they have different initial speeds. So they are falling at that instant through that point, but with different speeds. This means that also the laws of physics to which this principle refers will be independent of the velocity. Okay, so local freely falling frame refers to that, and local because it will be freely falling around that event, but when you go far away from the origin, okay, there will be deviation from this. All the non-local effects, tidal forces and so on will appear. Okay, and finally, there is a restriction to the non-gravitational laws of physics. The reason for this, first of all, is that there is no special relativistic theory of gravity, as we have remarked several times. So there is no point in extending this to the gravitational law of physics and saying that it takes the special relativistic form, because there is no special relativistic law of gravity. Also, this allows for the possibility that gravitational binding energies behave in a way different to other energies, something that still we don't know. The strong equivalence principle just extends this same formulation to all gravitational laws of physics. In particular, it says that all kinds of energy, including gravitational binding energy, fall in the same way or move in the same way in a gravitational field. An important observation is that if all the laws of physics have the same form at any time in the history of the universe and at any point in the universe, this means that the constants that appear in them, or what we usually think are constants, are really truly constant, and they have the same value along the history of the universe and across the whole expanse of the universe. So the Newton constant is really a constant, and you don't expect that it changes through the history of the universe. And the same should be true for the rest of the constants. This is something that people have tried to test, although this is clearly very difficult in time. It's easier to test in space, any possible variation of these constants across space. In particular, it's easier to do with the fine structure constant, because if there was any change in it, say in the next galaxy, which is far away from us or even further away, the light emitted by the particle, by that galaxy, could be different, I mean, for the same physical processes. And you can try to test this principle also in that way, checking the constancy of the constants of physics in across space and also time. We have argued that the weak equivalence principle suggests a strong relation between gravity and the properties of space-time. We directly look to the metric, and okay, we are going to try to show that the Einsteinian equivalence principle makes this relation between gravity and the metric of space-time even more likely. So gravity will be described through the metric, but it will be characterized by the curvature. We will see what is that. But we can advance that if you just look at the metric, remember that the same metric can take different forms in different coordinate frames. So just looking at the metric, you don't have an intrinsic description of gravity. You don't characterize gravity itself. You are the form of the metric is dependent on gravity and also on the particular reference frame in a very strong way. Curvature is less dependent on that. We will see how this works in more detail later. This relation between metric as a description of gravity and the Einsteinian equivalence principle is such that it is widely believed that only theories of gravity based on the metric, so in which the metric is the field that describes gravity, can satisfy the Einsteinian equivalence principle. It's extremely difficult that theories which are based on any other kind of field will satisfy it. Now let us study the consequences of accepting the Einsteinian equivalence principle. So here they are. The first consequence is that gravity is most likely described by a metric field G mu nu. This we are going to show in more detail later. Another consequence, which is less obvious, but I think it is very important, is that there is not a conserved local density of energy of the gravitational field. And here I remark the word local. So if you have a density of something and it is conserved, locally conserved, it means that this density satisfies a continuity equation. And that it is part of some current. Okay, so J0 is rho, and this current satisfies this continuity equation, which expresses conservation law, a local conservation law. Okay, well, this is not possible for the gravitational field, and it is not possible because of the equivalence principle itself. If we can make gravity disappear locally, its energy density will disappear also locally, and then it doesn't make sense to try to describe it by a standard density function. So this is just impossible, and okay, this can make you think that there is no conservation law of the energy of the gravitational field, but this is wrong because it is only the local description through a density of energy that is forbidden somehow, but the total energy of space-time and total momentum and so on, they will also be conserved, as you can expect. However, the absence of the local conservation is what you can interpret that this is what is behind the creation of particles of Hawking radiation and so on. You can violate locally any conservation law of energy, although globally energy will be conserved. The third consequence is that gravity bends light rays. This is kind of obvious because if you have something moving in a straight line and you observe it from an accelerating frame, you will see that it is curved, and you can interpret using the equivalence principle that the acceleration is equivalent to a gravitational field and that it is the gravitational field that bends the light ray. So this is something that you expect from gravity and which is not so clear to happen in Newtonian gravity once you accept that light is described by waves. So now let's discuss in more depth this first consequence. What we are going to do is to study the motion of a particle of mass m in a homogeneous and constant gravitational field. First we will study the non-relativistic case, and then we will study the relativistic one using what we learned a few videos ago. Okay, so let us start with the non-relativistic case. And we have a particle of mass m and a field of intensity, gravitational field of intensity g directed along this direction. This is a unitary vector. And the potential, the Newtonian potential, will be minus g u dot x dot, because then the force is just minus the gradient of phi. Then the potential energy will be m phi equal to minus mg u dot x dot, and the Lagrangian and the action of this particle will be 1/2 of m x dot squared minus v, which is plus mg u dot x dot. So this is t minus v, as you know perfectly well. Okay, the equations of motion are just x double dot I equal to GUI, or sorry, if I use indices, I don't use arrows. Okay, I find these equations of motion through the Euler-Lagrange equations, and I find that 2 factors of m in each side, and this would be inertial mass, this would be passive over active gravitational mass, and I know that they are equal, so I am already applying the weak equivalence principle, and then I can cancel them, and I arrive to this. So I know that the solution to these equations is if I choose the simplest initial conditions, x dot I at 0 equal to x I at 0 equal to 0, is just this accelerated motion only in terms proportional to t squared. Now we are going to see that when this motion is described in an accelerating frame, which will be a free-falling frame, particle moves in straight lines. Whether we choose these initial conditions or not. So the coordinates in the new frame will be given by this. This is the relation between the old and the new ones. Okay, observe that for this particular motion and with these particular initial conditions, the motion of this particle is that it just stays at the origin of coordinates all the time. With different initial conditions here or in y, the motion will be a motion in a straight line. But this is basically what we are going to see. We choose this particular free-falling frame. There are more falling frames, free-falling frames, because we could add to this other terms which correspond to different initial velocities, but we choose a particular one. And now, well, a second observation is that this transformation is certainly not a Poincare transformation, so well, it doesn't make sense in non-relativistic physics, so it is not a Galilean transformation, and it will not even preserve it will not preserve even the kinetic term. So let's see how this Lagrangian transforms. First we take a derivative. UIT, and from this we find that x dot I is equal to y dot I plus GUIT. Then we can substitute this and also this, okay, expressed in xi expressed in terms of y in the action, and this is a half of m y dot I plus GUIT square plus MGUI and then YI plus a half of GUI T square. Now we operate and we find first the kinetic term in the new coordinates, a half of my dot I y dot I, then the cross term with a factor of 2, so we have m g y dot I u I t plus 1/2 of m d squared. Now u squared is 1 because it is a unit vector, t squared, and then the terms that come from the potential, m g u I y I plus 1/2 of m d squared t squared. Okay, first these terms with t squared are total derivatives. Clearly they are the derivative of a term 1/6 mg squared t cubed. Okay, so they are total derivatives and they will give the same equations of motion, and we just remove it. Then if you look at this term, well, these two terms, they are another total derivative. They are the total derivative with respect to time of m g y I u I t. Okay, when you take the derivative with respect to t, one term has loses this t, and this is this term, and another term keeps the t but gains this dot. So it's another total derivative, and we can remove it because you get the same equations of motion as with this action, which is the action of a free particle, but now moving in a free falling frame, which is not inertial. Okay, so this is just a way to check that the weak equivalence principle is satisfied in this action once m, this inertial mass and the gravitational mass are equal. Now, an important thing is that now we want to see the relativistic equivalent to this, but we are going to start with the equivalent of this action. Yeah, the action that contains the kinetic term and already the coupling to the gravitational field. And we saw quite a few videos ago that the relativistic action whose non-relativistic limit gives you exactly this is an action that has this form. So now we have MC, the parameter lambda that describes the evolution, and we are going to replace wherever we have x dot 0 square instead of 1. Remember that we have 2v divided by mc square. Okay, and this is not changed, so this is x dot I, and here we have the square root. Okay, v is just m phi, and this is just, in this case, mg ui x dot I. So the action that describes the motion of the particle in this gravitational field is 1 minus 2 GUI xi over c squared x dot 0 squared minus x dot I x dot I. Now, there were two conditions under which from this relativistic action one gets back the non-relativistic one in this form, and one of them was that the speeds were low with respect to the speed of light, and the other one is that the energy, the potential energy of the particle is small with respect to the energy at the rest of the particle, mc squared, which in this case means that g has to be smaller than c squared. We said that this can be interpreted as the particle being coupled to, instead of the Minkowski metric, to a metric of the form y minus 2 g ui xi over c squared dx0 square minus dxi dxi. Okay, under these conditions it should be clear that this metric is also an approximation of this metric. Okay, now this metric is the Rindler metric. Now we're going to see that the Rindler metric is nothing but the Minkowski metric as seen from an accelerated observer's point of view. In order to simplify some of the calculations, I am going to choose a vector u, which will be minus 1, 0, 0. This minus is just a conventional sign, because the Rindler metric is usually written here as with a plus. So with this, the Rindler metric is nothing but 1 plus u gx divided by c squared dx0 squared minus dx squared minus dy squared minus dc squared. Now, I am going to ignore what happens to y and z because nothing takes place in that direction. The acceleration and the transformations are only take effect in the x direction. And instead of going from this coordinate system x0, x, y, z to a free-falling reference system that I will denote by x0 or ct, x, y, and z, but y and z are the same. Okay, I am going to perform the inverse transformations because it is a lot simpler. But once you prove that you can do it in one direction, it is clear that you can do it in the other one if the transformation is invertible, which can be seen to be the case. Okay, the transformation from the capital X t system to the small x and t system is given by this transformation, and x is given same factor plus x hyperbolic cosine of GTC. Now this SH is, I should write probably sinh and cos, but okay. In this context, there should be no mistake, and the notation is a bit simpler. So let's perform the change of coordinates from Minkowski to the Rindler coordinate system. Okay, so we just have to differentiate, and first with respect to x, I get the hyperbolic sine t divided by c dx, plus then with respect to t, first this factor c squared plus x hyperbolic cosine gt divided by c, and then g, the factor g divided by c. Then the derivative of x, the differential of x, is the cosine of gt divided by c dx plus c squared divided by g plus x g divided by c, and now the hyperbolic sine. Okay, now I square each of these two terms and I take the difference. So let me just look first at the terms with differential of t. I will get this square minus this one square, and it is hyperbolic cosine minus hyperbolic sine, which gives me 1, and then I only get these terms squared, so it's equal to c squared divided by g plus x squared times g squared divided by c squared and the t squared, and now this minus this squared, which gives me minus 1, so it is minus the x squared, and then the cross terms, which are equal in both cases, but so when I take the difference they cancel. Now I operate here and I get g squared comes here as g divided by c multiplied by c squared divided by g plus g divided by c x dt squared. Sorry, I should add c squared here, so this is c to the fourth, and this is c squared, and this is c squared. This cancel, this gives you 1. This is the x0 squared minus the xi dxi, which is the Rindler metric that we have seen here. Okay. So you can read this result now in two different ways. You are in the presence of a gravitational field, and this gravitational field is described by this Rindler metric. It's a uniform gravitational field in the direction of the coordinate x with intensity g, and then you can go to some free-falling frame in which you make this gravitational field disappear, and you get a gravitational field which is trivial because it is described by the Minkowski metric. Nobody tells you that this original metric, the Rindler metric, describes really a gravitational field in Minkowski. Sorry, if you want, in a flat space-time from the beginning. It could be that you are. This is just the effect of acceleration on a genuinely inertial reference frame, which is given by this one. You cannot distinguish between these two results. So you just know that there are two reference frames, the one with capital letters, this one, in which you don't see a gravitational field or inertial forces. This is just what you see. And another reference frame in which there is either an inertial force or a gravitational field. You cannot tell which one it is, and it is described by this non-trivial term in the metric. So now we can study this situation from a more general point of view. Instead of just considering a possibly uniform gravitational field or the inertial forces produced by a simple acceleration, we can consider the general situation in which you start with a Minkowski spacetime in some reference frame, and that by definition will be a free-falling reference frame, because the metric is the Minkowski metric. And now let's go to some other reference frame, which we call y, and which will be given by some functions y mu of y. Okay, we know that in this system, in this coordinate system, motion is described by this equation, which expresses inertia, and also supplemented by this condition which tells us that the particles that are moving are either massive or massless, and they move along time-like or null world line. Okay, now let's see what happens in this second coordinate system. What we do is we change the coordinates using the rules that I have given you. For any coordinate change. By definition, a metric transforms in this way, and by definition, this will be the new g alpha beta in the coordinate system y. Now we want to see what are the equations of motion in this new coordinate system y. Okay, so you have to take the derivatives. Okay, because this is, I remind you, this is just d squared of x mu d tau squared, where this is the proper time. Sometimes I write tau, sometimes I write s. So this is x dot mu, and using the chain rule, this is y alpha d tau. It transforms, as we said many times, as a contravariant vector, or the x mu dy alpha y dot alpha. Now let's consider the second derivative. And this is d tau of the first derivative, which we already know as this expression. Okay, first we take the derivative of the Jacobian factor with respect to tau, but we have to apply the chain rule. So this would be a second derivative of x mu with respect to y beta, y alpha, and then y dot beta, and the factor y alpha that we have here, plus the Jacobian factor and the second derivative of y alpha. Now, if this is the equation of motion, this will be equal to 0. And if this transformation is a good coordinate transformation from x to y, then the Jacobian matrix should be invertible. So we can this minus 1, we know that this is dy dx with the corresponding indices. When we take this equation, which is now the equation of motion of a free particle moving in Minkowski spacetime, but described in alternative coordinates y, and we multiply by the inverse of this will be y alpha. So I multiply, for instance, by y gamma x mu, because here it will give me just delta gamma alpha, and I will get, when I multiply this, then I will get y dot gamma, well, double dot gamma. So I get y double dot gamma plus partial y gamma partial x mu, and here partial square x mu partial y beta partial y alpha y dot beta equal to 0. Now these are clearly the general equations of the general form of the equations of motion of a free particle in Minkowski spacetime in an arbitrary coordinate system y. If you look at this equation from with special relativistic eyes, you would say that, okay, the best way to write it is this one. Okay, because this is how the equation of motion looks like. Remember that it was m y double dot equal to the force. So this should be interpreted as a force f gamma, and which kind of force? Because we know that we started from Minkowski spacetime. This force appears only because we are using a non-inertial reference frame. So these are inertial forces. The object that describes these inertial forces is called the affine connection, and it is denoted by gamma, gamma, capital gamma, and this one has indices beta and alpha. So we can rewrite this equation in this more general form. Okay, I have used the fact that this affine connection is symmetric because you can always interchange the orders of these two derivatives. So I put it in this conventional order. And in the literature, you will see this gamma written in different ways. So, for instance, this index could be written in first position. Okay, my convention is that I write it in the last position. There is an order in this indices: alpha, beta, and gamma. Gamma is up, but is in the third position. Now, in any other coordinate system, we know that this equation of motion of a particle should have exactly the same form. Maybe this object will have a different expression in a different coordinate system, but it will always have the same form. But also the interpretation of this gamma will be that of inertial forces or of gravitational forces according to the equivalence principle. Okay, so this this equation we have to learn, because it is the equation of motion of a particle that only moves under the effect of gravitational slash inertial forces. Okay, so it is a equation of motion of a free falling particle, Now, the fact that this equation should take the same form in any coordinate frame is something that you can check. You just apply the chain rule and collect whatever terms you find quadratic in y dot square, or the new if you go from y to y mu of some new coordinate c, and you apply the chain rule, you will see that you get the same form after you multiply maybe by the inverse Jacobian and so on. And if you collect the terms proportional to c dot, this will be the new gamma. The form of the equation is the same, but the expression of gamma is different in each coordinate system. This is what we understand by invariance. And then you will find, as we will find later, that this transformation rule for gamma, the one that is deduced from the requirement that this equation of motion takes the same form, so you just go from gamma to gamma prime, tells you that this gamma is not a tensor. Well, this is in agreement with the principle of equivalence, because if it was a tensor has the property that transforms homogeneously. It's always multiplied by Jacobian factors, which are non-singular matrices. So if it is different from 0 in one coordinate system, it is different from 0 in any other coordinate system, because vice versa, if it is 0 and you transform it, you will get another 0. This means that only if this guy doesn't transform as a tensor, you can set it to 0. And we know that in this particular case, if we perform the inverse coordinate transformation from the y's to the x's, we make it disappear indeed, and we get this equation of motion. The principle of equivalence requires that this is the case, because you should be able to make the gravitational field disappear at any point, at least locally. But this property that I told you about the tensors, if they are 0 at a point, they are 0 in some coordinate system, they are 0 at that same point in any other coordinate system, prevents gamma from being a tensor. Okay, so this gamma will not be a tensor. So what it is? Well, it is what we said. It is an affine connection, which is a field that transforms in a different way and has really a transcendental role in everything that follows, because it is the thing that describes the gravitational field. If you think of the metric as the potential of the gravitational field, somehow this is the field strength, or one step towards the field strength. Okay, because we will see this property that it is not a tensor is not very good to describe to be the field strength of the gravitational field, and we will have to find something better. But it is certainly a first step towards a field strength of the gravitational field. So let us summarize our results. We have shown that a description of the gravitational field in terms of a metric G mu nu is consistent with the Einsteinian equivalence principle. Okay. We have also shown that there is a quantity, an object, gamma mu nu rho, the affine connection that plays the role of field strength of the gravitational field, and that it satisfies an unconventional property that we can set it to 0 by going to a preferred frame or reference, which is what we call a free-falling reference frame at a given point. Okay, so locally we can do that, which is consistent with the equivalence principle, but which is quite unconventional, and probably we want something different to characterize the existence of a gravitational field, and that thing will be the curvature, and we will have to see what is that. We need some more maths in order to do that. Okay, if this is going to be the description of the gravitational field, we will have to consider other metrics that are not related to the Minkowski one by a change of coordinates. Okay. It is true that we can always locally make the metric g mu nu equal to eta mu nu locally, but this means that when you separate from a given point that you are considering, okay, so the point x0, there will be some other terms, okay, which are proportional to x minus x0. Okay, there will be corrections to this expression. So the only thing that the principle of equivalence demands from our metric is that you can go to a certain system of coordinates in which at a given point the metric is eta mu nu, but when you go to the neighborhood, there will be corrections proportional to x2 minus x0 or terms of higher order. Then we should be able to devise a framework in which we can work with general metrics that are not related to eta mu nu by any change of coordinate. In some cases, it will be as simple as replacing the Minkowski metric in the special relativistic action or equation by g mu nu. So, for instance, in the action of a particle, what we expect is that if this is the action for a particle moving in Minkowski spacetime, the action describing how the particle moves in any other metric, means in a general gravitational field and a general coordinate system, will be obtained by replacing eta mu nu by g mu nu, a general g mu nu that in general will depend on x. If this is the action, then using the principle of least action, we will find equations of motion that will have this form. Okay, if this is more or less guaranteed that we'll have a second derivative of the x's, and then terms which are quadratic in x dots. Sorry, this should be mu. So I don't know what this gamma is in general for a completely general metric, but by obtaining the equations of motion through the principle of least action, I will identify gamma with whatever terms I get with proportional to two derivatives of x mu. This gamma, as we will see, will be some function of the metric and maybe of derivatives of the metric, and we will check that the property that you can set it to 0 at any point by going to some free falling reference frame is correct. Now this is the equation that dictates the motion, or that will dictate the motion of a free falling particle, and here everything gravitational fields / inertial forces will be contained. Inertial forces will no longer appear in the right hand side of this equation. So all this will be defined as the proper acceleration of a particle. Remember that when we studied the law of inertia, we said that x dot mu transforms indeed as a vector under general coordinate transformations, but that x double dot mu does not. It only transforms as a vector under Poincare transformations. That was good enough for special relativity, but it is not good enough here. Okay, we have found a correction to x dot mu, x double dot mu, that now is going to transform covariantly, more or less, if you want, by definition, because we will dictate that this gamma transforms in such a way so as to make this completely covariant. Okay, so x double dot mu will be replaced by this a mu, and then if you multiply this m by a mu, okay, what you get in the right hand side when will be the forces, the external forces that act on the particle, and this will be the new form of the second law of mechanics in a general context. And now, important thing is that in these forces, not inertial forces are not contained, and gravitational forces are not contained. So in this equation, they are implicitly contained here, or if you want, they are not. They completely disappear from the equation. So free falling particle now is the same as a particle with vanishing proper acceleration. And this is the generalization of what you would call a free particle, and something with vanishing acceleration in the special relativistic context. Okay, and remember that now this is one of the most important things that you learn is in this video, is that gravitational forces and inertial forces disappear because they are automatically included in this thing. Something that moves freely, so only subject to the gravitational forces or inertial forces, because we are now free to consider any coordinate system, is now a free falling particle and has vanishing proper acceleration. Okay, and finally you see that we are finding that if we adopt the metric as the description of the gravitational field, it is natural to write all your equations in such a way that they keep their form under any general coordinate transformation, not just under Poincare coordinate transformations. So this gives rise to the principle of general covariance that we are going to see next. This principle of general covariance is something, if you want, independent of the principle of equivalence, but is more like a recipe to obtain the laws of physics which are in agreement with the principle of equivalence. So this is what we will see in the next video.